Different types of birds usually mate based on sound, or like songs and coloration. Because the thing is, in wild, a lot of times, the way that someone looks is, or an organism looks, is based on how healthy they are, right? Just like, for example, if you know that someone who is morbidly obese probably isn't the healthiest person because diets or whatever. Someone who is extremely skinny, we know, probably isn't healthy either because of lack of nutrition. So when we look at this idea, we are not, or we mate non-randomly because we choose, okay, here is someone who is neither overweight, really skinny, you know, they're average size. Okay, this person has, you know, what I go for in a person. They have whatever color hair, whatever color eyes. Birds do non-random mating. There's other species that do. Very little times are we going to see species in equilibrium. There are some, and we'll talk about some. But one thing too is with non-random mating, or with these, this is talking about populations, but it can also be talking about specific traits as well. Okay? Yeah, Olivia.
So like, what even is?
So let's think about this. Sickle cell anemia. Do we know who we marry? Well, we might know this, but let's say they're a carrier for it. They don't know it. Do we know it?
No.
What if we're a carrier for it?
No.
Is that mating randomly?
No.
Based on that trait, is it mating
Oh.
randomly?
Yeah.
Okay, that's random mating.
So that's considered.
And that would be considered a way where the equilibrium is intact because we're going through all the processes of not seeing any of that happening.
I'm really confused how random mating is equilibrium.
Because we aren't choosing which trait we want to see succeed. Random mating is all the alleles have equal chance to be passed on. Does that make more sense? Okay. Okay.
What couldn't random mating also like disrupt it? Because what if like two people got together and they had a kid who had like a bad disease or something? Like couldn't that still mess everything up?
Well, so I see what you're saying. So if it's a large population size, then if they don't have it, they're probably carriers, okay? Random mating occurs and their offspring has the disease. That offspring is going to be one of the small percentages of that population that has it. And when you look at the overall percentages, it should be balanced to where everything kind of equals out to where it needs to be, okay? So, any other questions from this section that I may not have answered in our little review here? Okay. That's not you all, don't get excited. What I want you all to do is go ahead, log on to Schoology and do your quiz, and you have 2 attempts. You don't do the exit slip yet because the exit slip is based off the worksheet and stuff after. So we will be doing the Hardy-Weinberg stuff here in just a little bit. Do your quiz. You have 2 attempts after unlocking for a second attempt. But you will have 2 attempts at it. Good luck. Day 32, yes. Day 32 quiz. Genetic change quiz. Once you're finished, you can close your iPads just so I know you're finished.
Bless you.
Okay, so the last thing we're going to do today is we are going to learn and talk about this Hardy-Weinberg equation. Because believe it or not, even though it might seem difficult by looking at this big long chart, it's actually not bad. Okay. So in this problem, we have the frequency of the dominant A allele being 40%. The recessive A allele is 60%. So essentially it says, what are the chances of the next individual in this population being born being homozygous dominant, heterozygous, or homozygous recessive? Okay. So all we do in this is you'll see the general equation here. P squared plus 2pq plus q squared equals 1. So this is just a little bit more of advanced than last time. Because if you think about it, last time, we added up the two allele frequencies, and what did they equal? 1. So last time, our equation was P plus Q, where we assigned the value of P to the dominant allele. Okay? So our dominant allele is representative of P. Q represents our recessive allele. Okay, any questions just with that? So in our original equation, we had P plus Q equals 1. Okay, so 0.4 plus 0.6 equals 1 in this example. So all we're doing is we are taking this and we are trying to find homozygous dominant percentage, heterozygous percentage, and homozygous recessive percentage. So here we see, to get the frequency of the homozygous dominant, we need P squared. So if I were to try to get P squared, and all I have is P, how would I get to P squared? P times P squared. Does that make sense to everybody? Mm-hmm. So in this situation, P equals 0.4. P squared would be equal to 0.16. Okay? Because that's 0.4 times 0.4. Is everybody following there? Any questions? Okay.
Wait, how did you get to point four?
Because it says the frequency of the dominant allele is 40%. 40% decimal form is 0.4. Okay. Q, we do the same thing. So Q in this situation is 0.6. What would Q squared be? 0.36. Good math. Okay. And if you don't know how to do that in your head, please use a calculator. Okay. You'll see a really quick example on your worksheet of why sometimes a calculator is better than trying to do it in your head, especially with decimals and square rooting decimals and all that. Actually, we'll do an example of it up here. You'll see. So the next step is to find 2pq. And this one's just 2 times p times q. Okay, so 2 times 0.4 times 0.6, and that's going to equal 0.48. Okay. Now all those numbers are representative of the percent chance of that genotype being present. So homozygous dominant, which is p squared, will be 16%. Q squared, which is homozygous recessive, will be 36%. 2pq, which is representative of the heterozygous, will be 48% chance to occur. Kylie.
I didn't do the math, but if you add those up, does that equal 1? Is that like what
Yes,
this is
ma'am.
doing?
And if we take p squared, which is 0.16, and we add it to 0.36, which is q squared, that's going to be 0.52. 0.52 plus 0.48 is equal to 1. That's how you can check your work. So what I want to do is, yes, this problem's right on the board for you. It's written out. I want to work through one problem with you, and then I'll let you all work on the worksheet together. If you all don't finish it today, that's fine. We'll pick it back up on Tuesday. Next Tuesday. Yeah, not spring break Tuesday, unless you all want to be on the beach talking about equilibrium. Probably not. So, what I want to say is, let's say P is equal to 0.7. P is equal to 0.7. Okay, so let's think about this. If all I give you is P, how do we find what Q is? Maddie,
Well, it would just be 0.3.
why is it? Where did you get 0.3?
Because if you're trying to get to 1 and you have 0.7, 1 minus 0.7 would be 0.3.
Did everybody hear that?
What if it's bigger than
Wait, why can't we just do it on the one first?
What if it's like,
What?
Okay, so all I gave you in this example was 0.7, okay?
Yeah.
So what Maddie was saying is that original equation that we worked on yesterday is P plus Q equals 1, okay? So if I give you the P is 0.7, the way to find out Q,
Yeah, like
1 minus 0.7,
Yeah,
okay?
yeah, like the first one we did, like just before that.
Yeah,
That was so much more, like not simple.
well, this is the beginning of the problem. So what we're going to do now, okay, is we're going to manipulate this. So we have our P and we have our Q. So you get how we got our Q, correct?
Yeah.
Okay. Is there anybody confused how we got the Q?
what if it's like a bigger number than just like 0.7? It's like 0.15.
It can be 0.15, it can be 0.18, it can be
It's the
0.5.
same thing?
Yeah, it would be the same thing. Okay, same 1 minus whatever point number you get. Okay, and like I said, you have a whole worksheet dedicated to this. So, and I think the very first problem it gives you 16%. Okay, so P is equal to 0.7, Q is 0.3. So how would I find P squared?
Sun has 0.7.
Times it by itself. So P squared is equal to 0.49. How would I find Q squared? And what would be the answer? 0.09. I knew someone would be sure on that. Because remember when you multiply decimal spots, if you multiply one decimal spot and one decimal spot, yet you're going to have two decimal spots. It'd be 0.09. If you don't believe me, try it on your calculator. I promise it's true. Scout's honor. Okay? So then we do 2PQ. How do we do 2PQ? 2PQ.
0.3 times 0.7.
Yeah. So 2 times 0.7 times 0.3 is?
Wait, why didn't we do 2 times 0.49 or 2 times 0.9?
Because, okay, good question. Because 0.49 is P squared. 0.09 is Q squared.
Is that?
So that's not the same as P and Q. The P is 0.7, the Q is 0.3.
So then why did we square them?
Why did we? Okay. Because P squared, this number represents 49% of the population is going to be homozygous dominant. Q squared represents 9% of the population that's homozygous recessive. So then 2PQ is representative of how much of the population is heterozygous. So when we do that, we do 2 times 0.7 times 0.3,
I got 0.42.
0.42.
But then when you add that all up, it does not equal 0.09.
0.09 plus 0.49 is equal to 0.52. 0.52 plus 0.42
Oh, I
is 1.
accidentally did one of them.
Okay, gotcha. Okay. So is there any other questions about this? I know it's kind of tricky math, and that's fine. But like I said, we're going to pick this up next class too and do more examples because I know it's difficult. It's math, it's science. You don't like combining math and science. So is there any questions on this problem, or does it make sense? Do you want me to do another one?
Can you do one from our worksheet?
Yeah, why don't we do the first problem on the worksheet, okay? Or not the first one, the second one that actually has numbers, okay? That's fine.
Can we do number 5? It's like a word problem.
Well, let's work through the first one. So, hold on. Number 3. In a hypothetical population, 16% of people have sickle cell anemia. The population in Hardy-Weinberg, or the population is in Hardy-Weinberg equilibrium. Sickle cell anemia is recessive. So number 1, let's just work this problem out like normal. Let's not worry about the A, B, C, or D. But let's just work this out as normal. So, if it says that 16% have a trait, is that talking about specific alleles, or is it talking about the specific genotype? No, genotype was right. Okay. So sickle cell anemia, is it a dominant, is it heterozygous, or is it recessive? Recessive. Okay, we've talked about sickle cell many times. So, if it's recessive, is that 16% going to be the frequency of dominant allele A, or frequency of the dominant allele, frequency of the recessive, frequency of the homozygous dominant, frequency of the homozygous recessive, or the frequency of heterozygous? Which one would sickle cell, that 16% be? Not the allele. Yeah, correct. It'd be the frequency of the homozygous recessive genotype.
Yeah.
So let's read the question again. 16% have sickle cell anemia. So that means they have the disease, correct? And it says sickle cell anemia is recessive. So if sickle cell disease is recessive, how many recessive alleles do we need for us to have it? 2 recessive alleles. 16% have 2 recessive alleles. that homozygous recessive. So 16% would be representative of our Q squared. Okay? So, now, here's an interesting question. We have Q squared. We can't really work, can we work to 2PQ based off Q squared? Can we go figure out what P squared is just based on Q squared?
Oh, yeah.
How would we do it? What would we have to figure out?
You do point, or 1 minus 0.16.
Who said it? I heard it. Morgan. Good job. Everybody hear what Morgan said? We have to find Q. So, and yes, you're right. I see you mouthing it. So if we had Q squared, how do we get to Q?
Square root.
Square root. Okay? So remember I said that what you have to do in this class for the math, you have to know how to multiply, you have to know how to do square root, and you have to know how to addition and subtraction. Right? So, to get to Q, from Q squared, we take the square root. So what is the square root of 0.16? Maddie, you said it out loud.
0.4.
0.4. So Q is equal to 0.4. And now we know Q is the frequency of the recessive allele. So 40% of the alleles in this population are recessive. Matt?
So that means P would be 0.6.
Exactly. Does anybody not understand why P would be 0.6? Okay. So, if we recall, P plus Q equals 1. I keep erasing on accident. We have our Q that's 0.4. So we need P plus 0.4 to equal 1. So what we do is we do algebra. We subtract 0.4 from both sides. 1 minus 0.4 is 0.6. So our P is 0.6, which is representative of the frequency of the dominant allele. So 60% of the alleles are dominant, 40% are recessive. Any questions so far?
So it always has to equal 1.
P plus Q will always equal 1. P squared plus 2PQ plus Q squared will always equal 1. Maddie?
When it says what is the frequency of the allele for sickle cell anemia, is that going to be our final?
For the allele is going to be Q. Our Q, because that's the frequency of the recessive allele.
So it would just be Q equals.
So it would be 40%. Okay?
We need to like memorize that chart.
This chart, no. If you know, honestly, if you know P plus Q equals 1, that's all you need. Anybody explain why?
I don't think I knew that was.
Yeah.
What? Okay, let's take a small detour and let's explain this. Because you've all have seen this before in algebra. What if I do this?
Is that 12?
If I square P plus Q, my answer is going to be P squared plus 2PQ plus Q squared. If I square 1, what do I get? 1. Which is why this equation can work. Does it make sense to everybody? So that's how we come up with this equation. So all you have to do really is if you can remember P plus Q, you can get to this equation. And then it's just a matter of working down from there. We have practice. Like I said, I promise. I see some of you all like, I hate math. Help me. Please, don't make me do math. We're going to work on this worksheet. We are going to do some more sample problems on Tuesday when we return. I'm not going to let you not understand this, okay? You all will be experts at Hardy-Weinberg, okay? And plus, this will also help you with algebra. So, we have Q, we have P. Can we find P squared now?
Yes.
So what's P squared equal to?
0.36.
0.36. So that's representative of the frequency of the homozygous dominant genotype.
Who has normal hemoglobin?
Yeah.
Yeah, who has completely normal hemoglobin. Yes, that is correct.
So that's 0.36.
That's
At
36%. But do people who are heterozygous have normal hemoglobin?
No.
Why not?
They're heterozygous.
But that means they have a dominant allele, right?
Oh, so they do.
They would. So we have to add those two together. Okay. So to find the frequency for heterozygous, it would be 2 times 0.6 times 0.4. What does that equal?
Give me a second.
Okay.
Yeah.
0.48.
What do we start out with?
0.48.
0.48, yeah. 0.48. So heterozygous people are 48%. Homozygous dominant is 36%. And homozygous recessive is 16%. So you should, based off all the stuff we did up here, be able to answer those questions below, A, B, C, and D. Do you all have any questions based on this?
C is P equals.
So what I want you to do, we don't have too much time left, but go ahead and take a few minutes. I'll stop you in a second because I do want to talk to you all about something. But what I want you all to do is go ahead and take a few minutes and just try to work through a couple of these problems. And if you have questions or if you're really struggling, just raise your hand and I'll come by and I'll help you out, okay? Go ahead and get started. Yeah.